morning. Today I'm going to start 555 timer. A 555 timer is actually an oscillator, or we call it as a multi-vibrator. Means it is meant for generating vibrations, multiple vibrations, multi-vibrator. That's why the name multi-vibrator. The 555 timer is one of the most popular and versatile IC ever produced. In 1970, Signetic Corporation, the company which the first time they introduced this IC into the market. It is a combination of both digital as well as analog circuitries. It is known as time machine as it performs multiple timing tasks, and it finds application in many places. Maybe it is generating no, in generating ramp and square wave forms. It can be used as a frequency divider, frequency multiplier, again voltage controlled oscillators. As I said, it is oscillators possible to generate oscillation of required frequency, pulse generators and LED flashers. There are plenty of application. I'll mention at the end again. Just to name few, I have taken here. So how it looks like, this IC has got very important features. It's capable of generating accurate time delays required for many application, from home appliances to industrial applications. So the IC looks like this. This is a 8-pin IC, and pin number 1 in the IC, starting with a notch. Near to the notch, pin number 1 is there. So ground pin is 1, trigger pin is 2, and output you take at pin number 3. Reset pin is 4, and 5 is your control voltage where you apply, and 6 is the threshold voltage. And pin number 7 is just to provide a discharge path for the capacitor. You have pin 7 where transistor is connected and given to the ground. So pin number 8 is meant for applying supply. That is power supply you apply at pin number 8. So this is IC, how it looks like. Same IC is available even in our crystal watches, quartz crystal. You can see here, this is how it looks like. Internal part, if you see in quartz crystal, it looks like this. So you have a timer here and no timer microcontroller chip here, which can be programmed to generate time delays. You have battery, you have a switching coil here, and you have a motor which will rotate needles in the timer or watch. Okay, so this is a internal structure, circuitry, how it is built and how it is assembled, and you can see when you open it. Okay, so this is one practical application where everyone can try in the home, that the application of 555 timer that is used in the quartz clock. You can experiment with the old wall clocks available in the home. Maybe older one maybe may not be working. That kind of pieces, if you have quartz crystal pieces, just open it and see at least, and you should be able to name the parts at least at this level. So just I'm mentioning this because this timer IC has got plenty of application. This is one I have shown is just an example of simple application where it is available. So by timer details, the discussion will do it. So to begin with, again, same pins we have mentioned here: ground, trigger, output pin, reset pin, and right hand side you have pin number 8 power supply, 7 is discharge, 6 threshold and control voltage at the pin number 5. But internal circuitry is important. So what are the main components or the blocks available inside the IC? These are the blocks. Two comparators you have, These comparators are nothing but op-amp comparators only. Op-amp we have discussed, so you'll be able to understand what is comparator. So op-amp is used as a comparator here. Means it compares two inputs coming at the input pins, right? So and gives the corresponding output. Which terminal input is dominating, that drives the output high. So that is what the comparator does, and comparator outputs are given to flip-flop, and flip-flop output is output of the flip-flop. You will be able to see the waveforms generated. Timer, multi-vibrator, we say multiple vibrations at the output can be achieved with this combination. This extra transistor is connected in the circuitry, which is providing a path for the discharging capacitor discharge path it will provide. And three registers, importantly on the top side you can see three registers of same value, 5k resistance, 5 kilo ohms of resistor you have, and this is fabricated in the IC itself. It is not connected externally. These three registers of 5Ks, that's why the name it has come as 555 timer, because it has got 5K 3 registers in it, and that works as no important voltage divider circuitry in the IC that provides one input to these comparators, because these registers are fixed values, and these fixed values will derive the voltage from the supply and apply the fixed reference voltages to these comparators. And another input you are taking care, you are applying from your end externally, and you are seeing the operation of comparators in the IC actually. So this IC can be operated into two modes. One is monostable mode and stable mode. Three modes, bistable also it is there, but we don't have much application, and it is out of scope. And monostable, stable only that are there for your study. So monostable is, mono means one. So one, this is also called as one shot multi vibrator, right? So and a stable multivibrator, when you say, it's a free running oscillator we call. A stable means there is no stable state, it runs freely continuously, you will get the wave generated at the output. We say it is a free running oscillators. So pin details I need not explain, because already I have told what is pin number 1 is what, pin number 2. Detailed discussion if you want to have, you can go through this. Directly I will start with a block diagram of this IC. Internally, if you see the block diagram, it looks like this. The two comparator what I shown, one flip-flop what I have shown, and transistor, three registers of 5K connected to VCC, and extra RNC that you are connecting externally other than IC. As a user, as a engineer, a design engineer, you are connecting the extra components R suffix A and C. Okay, so rest is given in the IC, and right hand side you can see the waveforms. I'll explain one by one. So just to make understanding simple, let me assume in the beginning that the capacitor voltage is 0, and I apply the trigger pulse at pin number 2 of the IC. Pin number 2, I hope you can recall. Pin number 2 is a trigger pin I have mentioned. When I say trigger pin, you are applying a trigger pulse at that pin. And what is there at another pin of comparator 2? Lower comparator, just you observe, comparator 2 we have mentioned. Comparator 2 positive terminal is connected to register, 3 register network actually, and these resistive network divides the voltage VCC. Suppose say VCC applied is 10 volt, 10 by 10 into 2 by 3 actually, 2 by 3 VCC that is available to the upper comparator, and 1 by 3 VCC reference voltage is available for the comparator to non-inverting terminal. Means what? You have set the references to the comparator. But what are the input, another terminal input for these comparators that we have to see? That we are trying to apply trigger pulse, that is negative going trigger pulse, right hand side waveform you can see trigger input. When negative going trigger pulse is applied and the magnitude of this trigger pulse, what I have mentioned, if it goes below 1 by 3 VCC, then only lower comparator output can go high. Why? How it is possible? Because its meaning is when trigger input goes below 1 by 3 VCC, means 1 by 3 VCC is available in another terminal of the same comparator, positive terminal of a comparator 2, that is dominating. The input at non-inverting terminal is dominating the input at inverting terminal. That is a meaning. So output goes high because of input at non-inverting terminal. So 1 by 3 VCC is greater than trigger pulse magnitude. Then output of comparator 2 will go high, and reset pin in the flip-flop. This flip-flop is 1-bit storage element, digital component element. Reset RS flip-flop we call, because you have set and reset pins at the input, and Q and Q bar complementary outputs you will be able to achieve. And whenever you say reset pin is high, Q bar goes high. Whenever set pin is high, Q goes high. That is only logic you try to understand at this stage. Again, fifth module I will explain in detail about it, digital part when we start. Okay, so time being, pin number 3 is connected to Q bar. Okay, Q bar is your pin number 3 and Q is connected to the transistor base. So I said that when you apply the trigger pulse and magnitude goes below 1 by 3 VCC, output of lower comparator goes high, reset pin is high, Q bar is high. When Q bar is high, pin number 3 is high, means output goes high. Output is high for at the pin number 3. When output is high, what is happening to the transistor and the capacitor voltage? When output is high, meaning is pin number 3, Q bar is high. When Q bar is high, complementary output at Q, it will be 0, it will be low, correct? That low voltage is connected, or low signal is given at the transistor base. Transistor is also in off state. In the circuit, you can say when there is no signal at the base or low signal, the transistor is in off state. When I say transistor is in off state, capacitor only it can charge for VCC connected through RA, but it cannot discharge, right? So that is a logic. Capacitor starts charging at the same time when you are getting the high output. So at the Q bar, when output is high, capacitor is charging for that period. Actually, you can see in the waveform right hand side, third waveform you can observe, right? So when this is happening, this will happen up to 2 by 3 VCC. Why? Because 2 by 3 VCC reference is set to upper comparator 1. Comparator 1, what I have mentioned, it has got the reference as 2 by 3 VCC. If VCC is 10 volt, it is 2 into VCC. 10 into 2 by 3 means it is 20 by 3. So the 6 point something, approximately 6 volts you can consider. 6 volts reference is available. Means what? Upper comparator output goes high only if the capacitor voltage goes above 6 volts. That is the meaning. Means when capacitor is charging here, up to what value it will charge? That is a question I'm trying to answer, right? So when capacitor voltage reaches 2 by 3 VCC, that is just exceeds 2 by 3 VCC at inverting terminal of upper comparator, means our input at non-inverting is dominating input at inverting. Comparator 1 output goes high, output goes high, and set pin will be set, and that's why Q will be high. When Q will be high, Q bar will be low. Definitely, Q bar at pin number 3 is low, means output goes low. Pulse second waveform, you can see output goes low. At the same time, when this is low, Q is high. Q high is connected to transistor base. Transistor is conducting, it enters into saturation, acts as a closed switch. So capacitor gets the path for the discharge to the ground. So that discharge is happening instantaneously. That's why you can see discharge, there is no delay. You don't have any delay here to observe. It instantaneously discharges because there is no resistance in the path for while discharging, correct? So capacitor directly connected to the transistor and to the ground, so we can say it discharges instantaneously. So this is charging and discharging. Once it discharges, it is output is low in low state. But again, when it will go to high state, only when you apply again trigger pulse with magnitude less than 1 by 3 VCC. Please keep this in mind. So what I'm trying to tell is output goes high only when you apply the trigger pulse with magnitude less than 1 by 3 VCC. Means what? Until and unless I apply trigger pulse, output will be in low state. Output is in zero state. It is in stable state. Only that stable state you can change by applying the trigger pulse. That is the meaning of monostable multivibrator, multivibrator with one stable state, right? Because it remains in stable state, low state, until and unless you apply the trigger pulse with magnitude 1 by 3 VCC. You can observe all this in the waveform. Again, one more waveform I'll display next after one more slide. So this circuitry, IC wise, how it looks, IC configuration when you do like this, and you'll be able to achieve the same. This is in block diagram form, and the same thing when you write in IC form. Directly IC utilize pin details, you know, and you connect the circuitry directly and generate these pulses. You can do that with the circuitry. Simple to look. If you remember the pin date numbers, that is enough here with the two R and C, two components extra connected to the IC. Otherwise, rest remains same. But internal block diagram, if you know, working, if you know, understanding is easy, and no need to remember things here. Easy to reproduce in the exam also, if you know internal working of it. To understand the internal block diagram working, you should know uh, understand this block diagram. So that is the idea why I took up that block diagram. Otherwise, this is possible. Yes, same thing written in IC configuration. Okay, so waveform, if you want a detailed waveform discussion, you can do here. You have a trigger pulse with magnitude 0, 1 by 3 VCC, 2 by 3 VCC, and VCC. So you can just mark these points, because trigger pulse, when you apply trigger, magnitude goes 1 by 3 VCC, below 1 by 3 VCC, then only you can expect your comparator output go high. That is lower comparator I am talking. And when lower comparator output goes high, reset pin is high, output goes high. So bottom waveform square pulse, what you can observe, this high state, and low state comes to zero. Zero state it is, low state is zero state. So you are getting one just pulse of some time duration. Here in this case, it is mentioned T is equal to 1.1 into RC, time period of on pulse, or it is charging period of a capacitor, one and the same, because when your output goes high, at the same time your capacitor is also charging. But I said already, in the block diagram, capacitor can reach up to 2 by 3 VCC, not more than that, right? So that is what it is marked here. So next, yeah. So next, this is derivation. We have seen the waveform. Looking at the waveform, you should be able to derive an expression. If you have understood the working of the block diagram, you should be able to write the waveform. If you know the waveform, you can easily start deriving basic expression for capacitor voltage. You know, it can be expressed. This VC is equal to VCC. Capacitor voltage is equal to supply voltage into bracket 1 minus e to the power t by r into c. Since I have connected R suffix A, RA register in the circuitry block diagram, what I have shown in the beginning, RA, right? So that's why I'm using RA term, okay? And C as it is. This minus e to the power minus t by RA into C indicates my waveform is exponential charging waveform. If you observe voltage across the capacitor, you can see it is exponentially increasing, charging, right? Towards what value? Towards 2 by 3 VCC. So that is the expression. Now, what is a maximum value capacitor can charge? It can charge up to maximum 2 by 3 VCC that I have discussed. So substituting for capacitor voltage in the main equation, first equation, VC is equal to 2 by 3 VCC. Substituting that same expression when I rewrite, it looks like this. 2 by 3 VCC is equal to VCC into bracket as it is 1 minus e to the power minus t by r into c, or RA into c. Please simplify this. VCC gets cancelled. 2 by 3 VCC, 2 by 3 on the left hand side, and right hand side you have in the bracket 1 minus e to the power minus t by rc. Take a natural logarithm of this exponential term, you will find the value for t, expression for t or tp, time period of a pulse, what you have generated at the output, that after simplifying, you'll get the answer as 1.0986 into RA into C. Or you can write it as 1.1 to be simple into RA into C, right? So this is the expression how you arrive at. Please remember the expression how you write for voltage across the capacitor. If you know that, what is the maximum value it can reach, that if you substitute, I'll get the simplified expression for time period of the pulse generated, or this is a period for capacitor voltage, also charging period of a capacitor also. So this will help you in solving some problems. Before that, just I will mention few application. Already in the beginning we have discussed some application. I mentioned few application. This we can discuss in detail if you provided, if you have interest, but because this is out of scope at your level, first year level, they don't ask these in detail circuitry and all. I don't want to discuss and make it complicated at this level. Just try to remember that this 555 timer in monostable, it has got applications like detecting missing pulses in the waveform, continuous waveform, and it is helpful in generating ramp waveform and all, frequency division operation and all. Yeah, one important application is PWM generation. It is possible with this 555 timer. So these are the circuitries in 555 timer operation. As I discussed, similar discussion we can do, provided you have interest, and if somebody want to do some what PBL projects, you can take up this circuitries and build it. And if you need any help, you can approach me. Yes, yeah. These are some application. important application. So next is a problem, simple problem I'll take up just to understand no, monostable multivibrator case. So in monostable multivibrator, in the figure shown, a register value is given, it is 100K and the time delay is 100 millisecond. Calculate the value of capacitor. So simple expression for time period of the pulse generated at the output, it's just T is equal to 1.1 into RC. When R is given and T is given, you need to calculate C here. C expression can be written as T by 1.1 into R. T is 100 millisecond and R is equal to 100K. So after substituting, simplifying, calculating, you will get 0.9 microfarad. 0.9 microfarad as the capacitor value for the given data. You will find this value. One more problem, one more example you can take up. A 555 timer in monostable multivibrator mode is needed to produce a time delay in the circuitry. If a 10 microfarad timing capacitor is used, then calculate the value of register required to produce a minimum output time delay of 500 millisecond. So you just write the expression what you have and the given data, given values are T is equal to no, time delay is given 500 millisecond is 0.5 microsecond, correct? So C is equal to 10 microfarad that is given in the problem, and the expression for time period of a pulse generated is 1.1 into RC. So please write the expression for register. R is equal to T by 1.1 into C, because T and C you know. Substitute and get the answer. You will get the answer as, check the register value, you will find, you will get it at 45.5 kilo ohms. So in the next class, we'll discuss a stable multi-mode multi-vibrator. That is second mode of operation of timer. Thank you.